First of all, we see nowadays the internet is dominated by the video. Over 70% of the traffic is video traffic, and the most notable one is the Netflix. Netflix consuming over the 30% of the internet traffic. Those kind of video on demand and live video streaming scenario, the requirements, the key problem is the bandwidth matters. So we can use the buffer to help. So we can see the exponentially increase of the value for those CDN companies, such as ECMA. But nowadays, to support this kind of live streaming, we have seen a lot of transport systems developed along with the timeline. First of all is the MPEG transport system. Then come to the HTTP live streaming, HLS. Then come to the Dash and the MMT. Now there are some other format is coming on for the next generation or the interactive streaming emerging. So the interactive, we have seen a lot of applications in the market already now. First of all is the Oculus. So Oculus is testing its cloud-based VR. And the second one is recently Google announced the cloud gaming to introduce the interactive video-based gaming, regardless of your device anymore. Then the third type is the Microsoft HoloLens and the Magic Leap. Even though they still need the local device, but eventually Microsoft's ambition is to bring all this kind of mixed reality to the cloud. And you can use very light glass or the interactive glass or interactive device to communicate with it. So for such kind of interactive applications, not only the bandwidth, but also the latency is a very critical issue. So we need a new transport framework that can take care of the bandwidth and latency jointly. And a lot of people to interactive with the virtual environment with the mixed reality in a very ultra low latency manner. So usually we have this kind of cloud deployed everywhere globally, geo-distributed. So the key question is like, for our contribution, also the key issues we want to resolve. First one is, can we find the best path from the remote server? For example, we have the AWS server in the North America, but we probably have the service in Korea. So how can we find the best path from the remote server to client in a real-time manner and to offering the lowest latency and the service sustainable bandwidth? This is the first question. And the second question is, giving a network path we choose, can we further enhance the quality of the experience of the client? Since the people, our human being or our consumer only concerned about the quality we perceived. We pay the money, we want the quality we perceived is the highest. The third one is considering the unexpected network dynamics. I don't know whether you already experienced this kind of when you in the subway or when you in the cloud, in the city. So you have the very dense population, you will have the large fluctuation of your mobile connections. That's the unexpected network dynamics. Can we adapt the stream in the real time to guarantee the QoE? So we want the quality as stable as we can. So for these three, the fundamental questions, we propose three solutions. First of all is the cloud overlay routing. Using this cloud overlay routing, we can find the best path from the remote to the local client. We also provide the collaborative video processing framework. This framework is to utilize the recent developed neural network to restore the high resolution quality to enhance the QoE. And the third one is, with respect to this kind of fluctuated network, we can use the adaptive real-time streaming. This adaptive real-time streaming also AIS is based on the reinforcement learning, using the past decisions to predict the future and improve the ability to combat network dynamics. For these three aspects, we will introduce one by one. I'm not going to go to very detail of the deep neural network design, but I'm trying to give the theoretical insights why we have this idea and how to resolve it. Of course, you can use different network structures or even different methodologies to resolve it. First of all, it's like overlay network. So usually we have the underlay network that we are unable to control it. If you specify the destination of a packet, and when you send it, you never know which path it choose. But thanks to the advance of the current cloud gaming, you can initialization, or you can call for this kind of Docker or the virtual machine on demand, using this Docker or the virtual machine to create the virtual routing. So this virtual routing is kind of like the overlay. So this virtual routing is like, for example, if you want to streaming the video from the North America to the Korea, you can choose the path from the Russia, or you can choose the path from the North Pole. So you can choose different paths, but which path gives you the best performance? The best performance means the lowest delay and the highest susceptible bandwidth. You can choose that one. So this is also supported by the very famous unequal triangle algorithm in the network. So when you have this network in deployment, the direct path is not only often is not the shortest path with the highest performance. You can choose different routing. So many people in the past try to resolve this kind of routing problem using the heuristic algorithm. Unfortunately, when you include more nodes or more virtual nodes, the heuristic algorithm is very complex. So we introduced the cloud overlay routing using the learning-based method. And using this learning-based method to maximize the ratio of the satisfied user. The satisfaction is based on the bandwidth we received at the user side. So here is the cloud overlay routing network. We're actually using a supervised learning. The supervised learning, you have the input from the past T slot. Each T slot have the n+2 times n+2 this metric. This metric is to note or record the available bandwidth and delay at slot time. So we have this routing decision model to decide the output of the n slot vector you can choose for the client. This is the cloud overlay routing. And the second one is the collaborative video processing. So usually we have this very popular video pipelines from the capture to the encoding and to the streaming and to the decoding. If you want the 4K video or 8K video, you have to capture at 4K and 8K and streaming at 4K and 8K. But instead, we propose a very interesting solution. It's like, can we downsample the video in the very beginning? So for example, we can capture the video at its quarter resolution or even 1/16 resolution, and using the learn the resolution scaling or the restoration algorithm to restore it. In the past, we only can using like handcraft interpolation filter, such as the bicubic or the age preserved. It can resolve a little. It can resolve a little issue, but with current the deep neural network, we can restore those missing high frequency information a lot. So with this approach, we still have the compatible pipeline with existing ecosystem. We all know that Japan will deliver the 8K program to the 2020 Olympic. But for most of the country in the world, the 8K stream is too huge. So we might want to use like a 4K or even like a 1080p to deliver over the network, but we can upsampling using this kind of learning method to have the almost a similar experience as the true 8K. Here is our CVP design network. We have this kind of supervised learning architecture. We have the we extensively using these convolution kernels in the residual network to ensure its fast convergence. And we have the high resolution and low resolution patches, random patches from random video. These videos we cropped from the YouTube, and we also have some videos we generated from the camera. And all these videos are collected together to training this kind of mapping function. And the third part is about the adaptive real-time streaming. Actually, this part of the research has been done extensively for the networking society. And first of all, we want to introduce the QoE metric for our target function or utility function. The target function is like the QoE for the network streaming is about the bitrate. So usually we have the high bitrate, high quality. This is a very fundamental intuition. And we also have this freezing penalty. When you play in the streaming, you will feel bad if the program is freezed. And also we have this kind of smooth penalty. You can't perceive this kind of program with large fluctuation. That will degrade your perception a lot. So with this QoE metric we defined, we introduced this reinforcement learning architecture to using the reinforcement engine, critical network, and active network to using past inputs. Past inputs include the receive bitrate, round trip time, and receive packets percentage, next and count, packet loss rate, and receive frame rate. So we include a lot of network QoE parameter, and also include a lot of QoE parameter to find this reward QoE. So with this kind of learning metric, we also introduce the recurrent network to capture the temporal variations and temporal dependencies to using this kind of temporal dependency to improve the QoE. Actually, this kind of network also be used by the year before last year, the SIGCOMM paper, Pensive, that developed by the MIT. The difference between our work from that MIT work is only for the VOD. So you have a lot of history you can track back, and you also have the knowledge of the future. If you have this like YouTube database or the Netflix database, you can trace all the segments, the speed rate, or the content quality. But for our interactive, especially for the cloud VR, cloud gaming, you have no prior knowledge for the future segments. So our framework has placed a lot of strict requirement for the learning. So we have some experimental study for the 3 parts for our Intel NET framework. The first one is the cloud overloading. We have simulated this 15 nodes topology, and right now we are deploying the practical servers in the mainland China. And we have the bandwidth proportional to the degrees. For this kind of simulation, we random pick up the servers and clients and adjust the number of the users to see the satisfaction rate. We can see that with this learning method and with the increase of the user numbers, our satisfaction rate increased significantly, about from the 5% to the 43%. And imagine that, especially in the mainland China, we have the mobile tower. We usually connect by over 1,000 people. It's much dense compared with other countries. So this kind of cloud overloading is very helpful for those dense population. And the second one is the collaborative video processing. We use it in the real scenario in the cloud gaming and compare with the HEVC, the most advanced video coding. In this one, we can see for the name here is the very famous gaming. So for the FIFA is the soccer, and for the WOW is the World of Craft, and Assassin actually is the 4K game used by Google Stadia. So all of these games are very high intense motion and with very vivid this color distribution. So you can see here we're using this CVP. We can have the rate distortion performance. The rate distortion performance is like under the same quality, how much bitrate saving. We can say over 30% saving we can achieve using this CVP. And we're still using the underlying HEVC codec. So we don't need to change the backbone for the HEVC delivery. And in comparison, we have the idea when we're doing the standardization of the HEVC. HEVC takes 3 years to finish over the AVC to have like a 30% bitrate gains. So, but with ours, we can quickly deploy it to a system. And the second one is now as I said, we can use the fake 8K. So we can have the 8K experience, but actually we deliver the 1/16 the 8K, not the entire 8K, since 8K consumes a lot of bandwidth. The third one is the experience study for our AIS, the adaptive real-time streaming. So this adaptive real-time streaming, we simulate the very typical network range, 4 megabps to 8 megabps in mainland China. For the US, the bandwidth is much better than in mainland China. So we're also using this live gaming scenario for the DMC, WoW, and MFS. NFS is the FPS game that requires very intensive interaction. So we have this simulation set up, and we compare with the most notable congestion control algorithm used right now in the entire internet that's developed by Google, say the Google congestion control. So for this kind of learning-based method, we can achieve like QoE over 57.8, and we have the variation decreased by almost 30%. So since we not only increase the QoE, but also decrease the fluctuation, since the QoE and this fluctuation also have both impact on the perception. Another one, we have plot this kind of time segments. We can see that the QoE value for our AIS is much better compared with the Google congestion control. Along with this kind of simulation studies, we have the practice in the wild. So first one is the any game. This is the direct competitor compared with the Google Stadia. We have the third-party independent test compared with the Google Stadia. We have a delay. We measure the delay in the same environment. For example, the Google Stadia delay is the 70 milliseconds, and the way using our neural adaptive processing has like 15 milliseconds. And for the bandwidth, we have the maximum is 8. Most of time it's much less than 8 megabps. And the Google Stadia has around like 15 megabps. And here is the, I think it's the demo using the car racing. I recorded a video. This is the server is central China, and we use it in the San Francisco airport. Somehow the projector is not very clear, so you can still see some artifacts. But if you come to see the screen, it's very good. The presentation. And we also have this kind of idea used in this kind of live interactive sports with the development of our own gigapixel camera. This gigapixel camera has a publication in the Nature and Optica. We use this gigapixel camera in the stadium. We installed several of them, and we can use it to capture the light fields of the entire stadium. And use the light fields, we can stream the light fields which angle you want user to want to perceive. So we have a lot of like data to transfer, and we have to make sure the latency is as low as possible. And here is actually our in the few years ago, we together with the PPC, US PPC, to broadcast the boxing. And here is with the NBC to broadcast the football. That's the football between the Duke University and the other university. So using the gigapixel camera, we can navigate. But in that time, we're only using 1 gigapixel camera. So you can see the navigation, but doesn't see the 360 around. So right now, we are trying to working with the Olympic Committee and to streaming broadcast the coming Winter Olympic in Beijing. So that one we try to use these facilities, and also using our neural network, neural adaptive transform. So in a summary, we designed this neural adaptive transport offers the successful service. We have this service provisioning for the cloud gaming already running in the mainland China for over 8 months. We have the direct competition, comparison with the Google Stadia, and have the superior performance over Google Stadia a lot. And it has like 3 fundamental resolutions. One is the cloud overrouting, another is the CVP, and the third one is AIS. As I said, we try to resolve this kind of high video delivery and ultra low latency in a way. But I believe there are a lot of other alternatives or methodologies. I welcome the discussion and welcome the comments. Thank you.